cost of die-cast and zinc fittings has reportedly risen by approximately 50%. This increase is a notable shift in the electrical materials market and may affect material selection decisions. The underlying reasons for the price increase in zinc-based fittings can be multifaceted. Firstly, fluctuations in the global price of zinc as a raw material directly impact manufacturing costs. Zinc is traded on commodity markets, and its price is influenced by factors such as supply and demand, mining production levels, geopolitical events, and currency exchange rates. Secondly, manufacturing processes contribute significantly to the final cost of fittings. Die casting, a common method for producing zinc fittings, involves specialized equipment, tooling, and energy consumption. Increases in energy prices, labor costs, or the cost of maintaining and replacing equipment can all lead to high manufacturing expenses. Thirdly, transportation costs play a role, especially for fittings manufactured overseas. Shipping rates, fuel surcharges, and tariffs can add to the overall cost of importing these materials. Fourthly, regulatory compliance can also increase expenses. If new environmental regulations or safety standards require manufacturers to adopt more costly production methods or materials, these costs are typically passed on to consumers. The question arises whether this price increase is prompting a shift towards the use of steel electrical metallic tubing or EMT fittings. While the price of zinc fittings has risen, it's crucial to consider other factors that influence the choice between zinc and steel fittings. Firstly, steel EMT fittings also have their own cost considerations. The price of steel itself can fluctuate, although it may not always correlate directly with the price of zinc. Secondly, manufacturing processes for steel fittings, such as stamping, welding, and galvanizing, involve their own set of costs. Thirdly, the availability and lead times for both zinc and steel fittings can impact project timelines and material selection. Fourthly, the specific application and environment play a crucial role. In corrosive environments, certain types of zinc or coated steel fittings may offer better protection against rust and degradation. Engineers and contractors must consider the long-term durability and maintenance requirements of each material. Fifthly, local codes and regulations may dictate the types of fittings that can be used in specific applications. Some jurisdictions may have restrictions on the use of certain materials due to safety concerns or compatibility issues with other electrical components. Sixthly, installation practices also influence the overall cost. Steel EMT typically requires different tools and techniques for cutting, bending, and joining compared to other conduit types. Installers need to be trained and equipped to work with the chosen material efficiently. Seventhly, the overall project budget is a primary driver of material selection. Contractors often weigh the upfront cost of materials against the long-term performance and maintenance costs to find the most cost-effective solution. To assess whether there's a significant shift towards steel EMT fittings, it would be necessary to analyze market data on the sales and usage of different types of fittings. Industry reports, surveys of contractors, and data from electrical distributors could provide insights into current trends. Furthermore, it would be valuable to compare the life cycle costs of zinc and steel fittings in various applications. This analysis would need to consider factors such as material costs, installation costs, maintenance costs, and replacement costs over the expected lifespan of the electrical system. For example, consider the installation of EMT in a commercial building. Firstly, the initial cost of the EMT and fittings is a primary consideration. Steel EMT is often less expensive than rigid metal conduit, but the fittings could alter the economics. Secondly, the labor required to install the EMT is important. It may require more supports than cable, but is generally faster to install than rigid conduit. Thirdly, the life cycle cost is very relevant. EMT is often galvanized to prevent corrosion. If the coating is scratched, the underlying steel will corrode. Fourthly, local electrical codes should be considered. Some jurisdictions may require certain types of conduit for specific applications or occupancies. Switching to a different type of fitting may require changes in installation practices. Firstly, installers may need training in the proper methods for cutting, bending, and joining steel EMT. Secondly, different tools and equipment may be required, such as specialized benders, cutters, and threaders. Thirdly, consistent installation practices are crucial to ensure the integrity and safety of the electrical system. Fourthly, proper grounding and bonding techniques are essential to prevent electrical hazards. When evaluating alternatives, it's helpful to consult with electrical engineers, contractors, and distributors who have experience with both zinc and steel fittings. These professionals can provide valuable insights into the performance characteristics, cost considerations, and installation requirements of each material. Furthermore, it's important to stay informed about changes in industry standards, codes, and regulations that may affect material selection decisions. Regular participation in industry events, training programs, and professional development activities can help electrical professionals stay up to date on the latest trends and best practices. Electrical metallic tubing, or EMT, is commonly made of galvanized steel or aluminum. The galvanization process coats the steel with a layer of zinc to protect it from corrosion. Aluminum EMT is lighter than steel but may be more expensive. The choice between steel and aluminum EMT depends on factors such as cost, weight, and environmental conditions. Rigid metal conduit, or RMC, is a thicker, heavier conduit than EMT. It is typically made of galvanized steel and is used in more demanding applications where greater mechanical protection is required. Intermediate metal conduit, or INC, is a thinner-walled conduit than RMC but thicker than EMT. It offers a compromise between weight and strength. When making conduit bends, it is important to use the correct bending tools and techniques. Firstly, proper bending prevents kinks and distortions that can reduce the inside diameter of the conduit. Secondly, smooth bends allow for easier wire pulling. Thirdly, incorrect bends can damage the conduit and compromise its structural integrity. Conduit supports are essential for securely mounting conduit runs to walls, ceilings, or other structures. Firstly, support should be spaced according to code requirements to prevent sagging or movement of the conduit. Secondly, different types of supports are available for different applications. Thirdly, proper installation of supports ensures the stability and safety of the electrical system. Conduit fittings are used to connect sections of conduit together and to connect conduit to electrical boxes or equipment. Firstly, fittings must be compatible with the type and size of conduit being used. Secondly, different types of fittings are available for different applications, such as couplings, connectors, elbows, and T's. Thirdly, proper installation of fittings ensures a secure and watertight connection. Pulling wire through conduit can be challenging, especially in long runs or with multiple bends. Firstly, wire pulling lubricant can reduce friction and make the job easier. Secondly, a wire pulling fish tape or rope can be used to guide the wires through the conduit. Thirdly, proper wire pulling techniques minimize the risk of damage to the wires. When connecting conduit to electrical boxes or equipment, it is important to use the correct type of connector. Firstly, connectors must be compatible with the type and size of conduit being used. Secondly, different types of connectors are available for different applications, such as set screw connectors, compression connectors, and threaded connectors. Thirdly, proper installation of connectors ensures a secure and grounding connection. Grounding is essential for electrical safety. Firstly, conduit systems must be properly grounded to prevent electrical shock hazards. Secondly, grounding ensures a low impedance path for fault currents to return to the source. Thirdly, proper grounding techniques minimize the risk of electrical fires. Electrical codes provide detailed requirements for the installation of conduit systems. Firstly, the National Electrical Code, or NEC, is the most widely adopted electrical code in the United States. Secondly, local codes may have additional requirements or amendments to the NEC. Thirdly, it is important to comply with all applicable codes to ensure the safety and compliance of the electrical installation. NEC Table 300.5 specifies minimum cover requirements for direct buried cables and raceways. This table provides guidelines based on voltage, burial location, and type of wiring method. For example, for residential branch circuits rated 120 volts or 208 volts, a minimum burial depth of 12 inches is typically required for direct buried cables. For rigid metal conduit and intermediate metal conduit, a minimum burial depth of 6 inches may be permitted in some cases. It is important to consult the specific requirements of NEC Table 300.5 and any applicable local codes to determine the correct burial depth for a particular installation. NEC Article 310 covers conductors for general wiring. This article provides requirements for conductor insulation, ampacity, and installation. NEC Table 310.15 B16 provides ampacity ratings for insulated conductors rated up to 2000 volts. This table is used to determine the allowable current carrying capacity of conductors based on their size, insulation type, and ambient temperature. For example, a 12 American wire gauge or copper conductor with THHN insulation has an ampacity of 30 amps in an ambient temperature of 30 degrees Celsius. The ampacity of a conductor must be derated if the ambient temperature is higher than 30 degrees Celsius or if there are more than 3 current-carrying conductors in a raceway or cable. NEC Section 310.15b3 provides adjustment factors for ambient temperature. These factors are used to reduce the ampacity of conductors when the ambient temperature exceeds the values listed in NEC Table 310.15b16. For example, if the ambient temperature is 40 degrees Celsius, the ampacity of a THHN conductor must be multiplied by a factor of 0.91. NEC Section 310.15 code provides adjustment factors for the number of current-carrying conductors in a raceway or cable. These factors are used to reduce the ampacity of conductors when there are more than 3 current-carrying conductors in a raceway or cable. For example, if there are 4 to 6 current-carrying conductors, the ampacity of each conductor must be multiplied by a factor of 0.80.